Question? Any concerns? You know about the field trip, right? Half of the class is lecture. Thursday and the half lecture. Friday. Alright. First we will talk about the part that we skipped last time, okay? About the self.
Morning. Hello. Anybody out there?
Go and bring your ID card. You're gonna check and have it signed.
Okay, we got a lot of ground to cover today. So let's take a roll. I apologize for not being here last week. I'm working 4303 class and 4305. And on Thursdays they meet on the same day. So whichever one pays the most, I show up. We want to talk a little bit about ethics in facility design. You're wondering how in the world do those two things go together? How do you tie those together? What's the connection between them? Oh. This video will show here. We're going to talk about being a registered professional engineer. The film clip I'm going to show you is from 1937, and I hope the sound comes through. Okay, so we had a glitch on the sound part. New London, Texas is located in Far East Texas. In 1937, a new school had been built. It had been in the East Texas oil field. They had a brand new building. The building exploded one Thursday afternoon. A few of the kids had got to go home earlier, but over 300 students and teachers and other people in that building were killed as a result of a natural gas explosion. This film clip is a little grainy. Remember, it was shot in 1937. HD hadn't been invented yet. But it affected an entire community. It was as a result of this disaster that registered professional engineers were made, the ability to have registered professional engineers came into law by the Texas legislature. So let me stop the video. Like I said, it's kind of grainy without the sound coming through there. What they had done was the East Texas oil fields had just come into play. There was lots of natural gas. They built this new school building with the oil revenues. Things were really looking good. The school had been designed with a boiler system in place where you heat up water and then put hot water through the pipes. And, the pipes were connected to radiant heaters in each of the classrooms. Somebody decided on the school board that there was all that natural gas. Let's just use natural gas heaters. And we'll run a line from the oil fields, so they tapped a line a company provided a line coming from the field separation, to run that gas into the school, and they put gas heaters in each classroom. There was no engineering design on it. So the classrooms had this natural gas piping into every classroom. There were leaks in the building, but they weren't detected. Natural gas has no smell. When you say you smell gas, like in a municipal line, it's because mercaptans have been introduced into the line as a safety feature, so that you can smell that gas. Because natural gas will have no smell, it permeated the whole school. Some of the kids earlier had reported that they'd been getting sick. That natural gas had a leak in the sub-basement of the building. It built up. There was a vocational class going on. They said an instructor fired up an electric sander. The arc on the motor set off that gas, blowing up the building and killing over 300 people. So the state of Texas, as well as all states in the United States, recognize a professional engineering certificate. That certificate is granted when you graduate from an accredited university. Texas Tech is accredited. You pass engineering exams, have a certain amount of experience that's required by the state, and then you're granted a license to practice as a registered professional engineer in that state. And this is a certificate. That's mine, granted in 1979. I was number 46,300 or something. I believe the number now has been issued is up to over 150,000. There is a code of ethics for professional engineers. These slides come from the National Society of Professional Engineers website. But if we look at the preamble, I want you to look at it. There's a few key words that we go in here talking about what is expected of a professional engineer. And some of the key words is sanitary work. So look at the first thing they talk about is it says that we're to exhibit the highest standards of honesty and integrity. Engineering has an impact on the quality of life for all people. You're required to be honest, impartial, fair, and equitable, dedicated to the protection of public health, safety, and welfare. Engineers must perform under standards of professional behavior that require adherence to the highest principles of ethical conduct. Where in there does it say you have to know what you're doing? It doesn't, does it? It doesn't say you have to make an A in the facilities class. Just have to have that degree that says you have passed those minimum requirements for engineering work. But in the canon of ethics or the code of ethics, all of the things that are talked about is how you behave as an individual, how you portray yourself to the public, keeping in mind that everything you do is for the first and most importantly, for the safety of the public. So these are called the canons. There's a lot of slides here with a lot of words on it. I want you to go back and you can read them later. We're not going to go through all of this in class. But most importantly, to hold paramount the safety, health, and welfare of the public. Who is the public? Yeah, that's anybody. And more importantly, when you're in the oil field, it's your co-workers and fellow employees. So everything you design and put out there has to be done with safety in mind, because it's not just some ambiguous person that may come on the lease. It's the people you're working with. And then these are in the rules of practice. Here's another one that's really key and important after safety, health, and welfare is to practice. Engineers shall perform services only in their areas of competence. So you're trained as petroleum engineers. And especially when we talk about facilities design, there's lots of areas of that facility and things that we'll build and talk about that we're not going to talk about in petroleum engineering classes. For example, electrical installation, structural requirements, civil works for roads and foundations. All of those things are a separate discipline of engineering. If you want to take those, you take civil engineering, mechanical engineering. So there may be parts and pieces of that facility you're going to have to go somewhere else to get that technical skill or have those people with those technical skills perform those duties for you. There are areas of competence that you will develop as you go through your career, and certain things you'll have a good understanding, a good knowledge of that area, and so it may not be necessary to bring the mechanical engineer in and verify that particular part of it if you feel you have that competence. But remember, by you signing off on it, you're saying, I'm guaranteeing your health and safety. These are the professional obligations. They look very similar to some of the codes and canons that we've already talked about. But in summary, being an engineer, you have a responsibility to protect the safety and health of the public in the design and operation of a facility, whether you're licensed or not. If you're licensed, that means you can represent yourself to the public, you can take on independent work, you can be a consultant, you can sign government documents, you can sign certified documents where necessary to be signed by a professional engineer. A lot of you will work in companies where that is not required. You work under what's called a industry variance, where you're allowed to do the engineering work without having to be a professional engineer. The company is taking that liability umbrella under its own venue, and they're saying that we'll attest that our engineers are doing this safely. But if you're working for a company that's working on BLM lands or state lands, where a state or federal government wants to sign off by a registered professional engineer, you have to be registered to do that. So the public includes your coworkers and fellow employees, the people you're sitting with here today, and some that you haven't even met yet. Know what your limits are on your area of expertise when it comes to facility ethics. Questions? Okay, I understand you went through some of these pretty quickly. On facilities, one thing I've noticed, most of the time when we go through facilities, every one of them are sitting by a road. There's access to that by the public. So just because it's in the oil field, not everybody out there is an oil field worker. There's hunters that will come out and will be hunting. There's people that drive up and down the oil field roads for places to party, all those kind of things. There's going to be lots of reasons that lots of people are out there. It could be a school bus dropping off some kids for a tour. All of those things have to be designed with safety in mind. And we looked at some of those earlier slides, lots of batteries, lots of equipment, lots of facilities. A tank battery can be as simple as this. And one thing, this is where some of you get tripped up in senior design, is you learn how to design all of these vessels, and you think, I got to use every one of them in my battery design. But like this facility here that's got a couple of oil tanks, a water tank, some separators, and a heater treater, that's all they needed at that particular battery or facility to do the work. Don't over-engineer it. Don't put too much in there that you don't need. So this was a simple battery, required very little equipment compared to some of the bigger picture ones that we saw with a lot of pictures on. Tanks. This is a tank battery. All it has is a heater treater and 3 tanks. Probably, again, 2 oil, 1 water. That can be a battery. It works as a facility. Compression, we're going to talk about that. A lot of these things we will see live or in work or at OTC. We've added compressors that you guys haven't seen yet. Some of them with internals with plexiglass plates over them so you can see those interior working parts. Again, lots of tank batteries. Notice they've all got a road volume. This is one of a gas well, a high pressure gas well. It's got a wellhead here, a tank probably for water, and a separator. And then here's another view of it down here, going on down to a gas sales point. We're going to talk a lot about gas sales here in a minute. But notice how simple that can be. Notice how far apart things are. It's probably this is at least 50 feet from this wellhead to that separator. There's minimum distances we need to space equipment for fire safety, explosion safety. What you'll see at OTC, things are condensed together because we're not putting anything through them that's hazardous. But in practice, these things have to be safely spaced. Either there will be a state or federal standard on that, or there will be a company policy on how far apart those vessels need to be. Sooner or later. Again, more samples of batteries. These are gas sales meters. This is where your cash register is for your sales of gas off any given lease or property in those meters. Notice that there's two. There's one here. There's another one here. Probably the gas company has a meter that they will use to collect the volumes and sell the gas, and the company may have a check meter. You're the operator. You want to make sure they're not doing, they're not getting any mismeasurement here, so you put your own meter in there as a check meter, just to double check on that volume that's going through there, because this is what you're getting paid on. The other important part of this that we need to think about is the quality that's going through here down the sales line, and also the pressure that's at these points on this battery. Wherever this goes into a sales line, there's a pressure behind this that is set by the gas processor or the gas pipeline company. That pressure is your starting point for your design through your battery. Because everything we do, if the gas is flowing this way, has to be able to get into whatever this pressure is right here. So that's our starting point. And we negotiate that as part of the contract. It may not be negotiable. There's only one gathering system in a given area. That pressure is set at that point if it's 50 psi or if it's 1,000 psi. That's going to be set in our contract, and everything we put in there has to be designed to be able to meet that requirement. If we can't get into this line, we don't sell the gas. We don't sell the gas means we don't sell the oil because we're shut in. So this is critical. And again, a little review back maybe from what you covered earlier last week. Keep coming in here once a week. It's going to be a good deal. I won't know what you talked about. Here's our gas sales coming through here out in the simplest case through a separator and going to gas sales. That's that back pressure point. That's our sales point. That's our cash register. Just like off the oil tank, here's our oil sales. So this is where we're making our money, where we're selling it here and where we're selling it here. If the gas doesn't meet the minimum standards for quality, it doesn't meet the minimum pressure, it doesn't move. Same with the oil. You look a little bit at the flow streams for high temperature, low temperature wells. Some tank batteries will have a high-pressure gas system, and some will have a low-pressure system. This is not uncommon, especially in offshore platforms. Also, where you have a gas lift system, where you're pressuring up some of the gas. You know, if you look at this closer, there it says a low-pressure gas line, that says a high-pressure gas line. So the high-pressure gas line may be taken off, going back for gas lift wells. It may go for additional compression. The low-pressure gas is where we're selling it. What's high, what's low? Well, generally in an oil field gathering system where we have oil wells, we're using pumping units, we're producing the tank batteries, that line pressure is going to be on the order of 50 psi, certainly less than 100 usually. It's not uncommon in gas fields to have 500 to 1,000 psi line pressure that we have to meet. We may be able to meet that requirement just by the natural flowing pressure of the well, and then as the well's depleted, we may have to add compression to get to that. So those are the order of magnitude of numbers that you'll be looking at for pressure. Okay, slides with lots of words. Love all this. Okay. A gas contract may have 20 pages to it. And a lot of that will be written by lawyers, and hopefully with your help as an engineer. A lot of the gas contracts are already boilerplated with so much set language that's been agreed on by decisions in law over the years. There won't be much to change it, but there will be things that will be negotiable in every gas contract. But once you have signed that gas contract, that's what you're going to live with through the remaining life of that field. So at the delivery points, that's where we're selling the gas. We'll have language in here. It's got to be free of dust, hydrocarbon liquids, water, other contaminants that might have come through the system. And dust may sound strange to you, but you literally can get dusty gas. Not sure how that happens, but I have seen lots of dirt build up in some gas lines. Part of it is, corrosion products probably that have made their way through the system to the metering points. There will be pages of specifications where we look at specific elements. We'll look a little longer at these. First of all, we don't want contaminants in the gas, and especially hydrogen sulfide. And then you will also see CO2, nitrogen called out, and then this has a temperature specification on it. Why do we not want contaminants in the gas sales?
Damages the line, and the company doesn't want to pay you for things that they can't sell.
Okay, first of all, it damages the line. What's the problem with H2S? It's corrosive, isn't it? You take H2S and some water, mix it together, get sulfuric acid, it'll leave the metal. The same with CO2. Carbon dioxide forms carbolic acid, eats away at pipe and metal. What's the other danger with hydrogen sulfide? What? Poisonous, yeah. Hydrogen sulfide is super dangerous. We'll look at some charts in a moment. We'll get into that. The other thing that it says is we want to be free of oxygen. Why is that? Huh?
Fire.
Okay, fire, it's also a corrosive element. If we have water and CO2 and we don't have oxygen to mix with it, we can't do the chemical reaction to get the corrosive element. So oxygen, we keep keeping that out, we're keeping the corrosion down. We're doing ourselves a favor if we keep all these things out of that gas too, because it's got to go through our equipment. We've got to do the right things to settle it out, because our equipment's going to corrode just like the pipeline company will have the corrosion problems. Notice that the H2S is here, it's mentioned at 75 grains per 100 cubic feet. We'll see it expressed as parts per million. There's some conversion factors we'll look at in a moment. But CO2 can be higher. And CO2 reacts with water at higher partial pressures, depending on how much that CO2 is of the total gas stream. And so we can take a higher loading usually of CO2 than we can H2S before we encounter problems. The other problem I mentioned is we can't sell it, because what happens if we take these other compounds, and these are generally called inerts. The CO2, the H2S, the nitrogen are called inerts. If we mix them with methane, what have we done to the heating value of the gas? Huh?
Lowered it.
Yeah, we brought it down, haven't we? So the pipeline company doesn't want to buy gas from us that has high inert volumes in it. I've seen one place where they really did want high volumes of inert gas. And it was because they were taking some very rich gas from another part of the field. They were bringing it into the plant. They took a 30% CO2 stream from wells that we were producing, and they combined them, and they diluted down the rich gas with the inerts and got 1,000 BTU gas and sent that down the pipeline. Control the oxygen, don't have the corrosion problem.
Who gets rid of the H2S?
Either we'll have to do it, or the purchaser will have to do it of the gas. Depends on how our contract's written. You might be able to sell it battery with H2S. This is another pipeline spec. These, you wouldn't find all these in the same contract, but it talks about grains of total sulfur that can be there, the grains of H2S. This one doesn't allow more than 2% CO2. And then it says residue gas delivered at the pipeline, not more than a total of 3% by volume of all 9 hydrocarbons. What is residue gas? You've probably heard associated gas. Residue gas is what's left after processing. So that's generally what goes to sales at the tail of a plant. So we call it residue. The plant will separate out the NGLs, the natural gas liquids, separate out propane and butane, and then residue. Residue is very close to pure methane. So you'll see that term used a lot in the contracts. Another point that's real critical is shall not contain more than 7 pounds of water per million standard cubic feet. 7 pounds of water per million. Why is the water content important? Okay, it can freeze, can it? And what else? It's one of those products that help make corrosion. It's going to be part of the corrosive chemical reaction. So we've got to keep the water out of it. This one has a temperature that says we can sell between 40 degrees and 120 degrees. If we get real hot gas from a hot well, we may have to cool it down before it goes to sales. Something can go wrong. Something can go wrong, usually will go wrong. You've got to have some way to negotiate how to correct that. That'll be in the gas contract. The measurement of the gas is critical. It will be specified in the contract how the gas will be measured, what type of meters will be used, who will be responsible for calibrating them. There is an American Natural Gas Association Report 3 that is kind of the Bible of gas measurement and where how sale gases are determined. Here's another way these elements could all be specified. This one's laid out kind of nice and neat and in tabular form. Talked about water vapor, hydrogen sulfide, total sulfur, temperature, carbon dioxide, oxygen, and nitrogen. That's laid out pretty handy for you. These are conversion tables for all the ways H2S can be written, or in all the units of measurement and how you can convert from one back to the other. Those will be important to you. H2S is dangerous. The mercaptan that's put in there will smell similar to H2S, the rotten egg smell. But at 10 parts per million, you're safe for 8 hours of exposure. That's what OSHA says. You work in the oil field every day, you get that 10 parts per million, you go home, you reset, come back the next day. You may have a headache, might feel a little dizzy, but you're all right. Been there, done that. At 100 parts per million, though, your olfactory nerves are dead. At that point, I don't smell any H2S, it must be all right. That just means you're already past the 100 part per million threshold. Now you can't smell it anymore. Now you can't rely on your natural senses. That's why you'll wear H2S detectors on your clothing in the breathing space when you're working in the field that has H2S in it. And you see a higher concentration, it can be lethal. This is an important contract spec here where we talk about gross heating values. And generally we want 1,000 BTU per cubic foot of gas. Remember I told you some areas had it higher, they would dilute that down where they could sell that total gas stream. So there will be a range specified in your contract that you'll have to have gas that will meet those qualities. And then the measurement and testing, we'll talk about different kind of meters in here. There's certain kinds that can be used for gas measurement. Some are more accurate than others, and what usually happens when you get a more accurate meter. I could get this meter, not as accurate. I can get this meter more accurate. What's the difference? Cost. So you got to have something that fits the economics of where you're at too. There's lots of things you can do, but you may not be able to take the cost of doing it. This talks a little bit about the meters. More about the meters. Let's get these questions. Let's talk about revenue from a gas stream. This will be important to you here for the economics of what you're doing, also in your design projects that you'll be bringing this through. We'll have to have a gas analysis that determines the BTU per standard cubic feet. There's only one way to capture that and get it. You can get it on automatic measurements, but the equipment is very costly to do that as opposed to taking samples. It will have to be metered at a contractual sales point, and then there will be a percent or differential from a reference price. So if I'm saying I'm selling the gas right here, the cost may be based on a market in Oklahoma. I might have to take a deduct to that market because of transportation. So our price reference points are generally in the U.S. at the Houston Ship Channel, Henry Hub in Oklahoma, or Waha in West Texas. Waha, the gas goes generally on out to California to the population centers on the West Coast. Henry Hub can go to the mid-continent. And Houston Ship Channel usually has the pipelines that can take it all the way up the East Coast to New York City. Kind of counterintuitive, you already got in Oklahoma going up. But a lot of those pipes, we'll see in a minute, run out of Houston. So let's look at an example of how this would work on the calculation. We have 10 wells. We got 3 million a day per well, 8 barrels of oil per million cubic feet of gas. We've got a 1250 BTU, that's kind of a rich gas. And then we've got a Henry Hub price of $8.53. That was taken a few years ago. Gas today is about $3.50. Same gas hit $15 in Chicago. But that didn't last long, and it was a pretty cold winter. Our oil price will take it $59.50. And then as gas goes through pipelines and plants, there will be what's called shrinkage. And most of that is fuel gas used by compression or fuel gas to run treating equipment in the plant. And you're going to have to take that loss in your gas stream as part of your contract to move the gas. So we have a shrinkage on this one. We show a contract also that is gas price is Henry Hub less 15 cents a million BTU, not per MCF, but BTU. You gotta watch yourself switching back and forth. What's chargeable on a volumetric basis, what's chargeable on a heat content basis. And in our oil contract, we have a $2.50 charge on that, probably for transportation. So the gas revenue and the oil revenue are straightforward calculations. The gas revenue is our total gas stream, 10 wells times the times 0.95, that took care of what? Shrinkage. Times 1.25, that's our heat, times our number of MCF. And then we had a 15-cent deduction on our price per MCF. So this gives us this much per day in gas revenue. Straightforward calculation. What have we not accounted for in that calculation? What assumption have we made?
Price differential?
No, we got the price differential. Difference between gross and net. What's our royalty on this? Okay, we can only do this to our share of the stream. We may do it to 100% of the stream, and we have to pay royalty out of this. So there's no royalty taken out of this. This is showing only the prices that it affects that cubic foot of gas coming out of the ground. Oil revenue the same way. This is the total volume. This is a ratio measured based on testing that's done, 8 barrels per million. Here's our deduct on our quoted price. Gives us that much revenue per day. Total monthly revenue, everything's done on a daily volume, so we add our gas and our oil together, times average 30 days a month, and we've got that much revenue per month to work with. Straightforward? Now, in our revenue stream, sometimes when we go to a gas plant for handling and processing of our gas, you'll have what's called a percent of proceeds contract, called a POP, P-O-P, percent of proceeds. So the proceeds that we get, the gas plant is going to keep some of that for providing us that service. 150 million a day gas plant probably costs $10, $15 million. They want their money back. So they're going to charge us for doing that. So a processor will usually keep, on this order of magnitude, 10 to 20% of the residue gas. What's the residue? Yeah, the gas that comes out the tail end of the plant that's been processed. They're going to keep 10 to 20% of that as a fee for bringing the gas through. They will take, on average, about 50% of the propane and butane that they extract out of the plant by processing, and they'll keep about half of the revenue or less from the NGLs or gasoline that they might extract to it. That 1250 BTU gas that we put in there probably has some gasoline component in it that could be pretty readily pulled out. So the richer the gas, the more this will be, the more the plant's got to process. And these are order of magnitude numbers that you'll see where you have a percent of proceeds. So if somebody tells you they got an 80-20 pop, what would that mean? Huh?
They get 20% of it.
Yeah.
You keep 80.
You keep 80, they keep 20. So an 80-20 pop is an 80% revenue that you get to keep. Now, the processor has to allocate all these revenues and volumes back to the delivery point. There's about 65 of you in here, and every one of you's got a gas meter sitting on your desk. And you're selling gas to me. I've now got to account for 65 of you bringing your gas volumes in here. And your gas has 1 million BTU per MCF. And your gas has 950. And yours has got 150. And you've got 125 or 1,250. Now I've got to weight the BTU content of that coming in here and make a distribution back to you of your share of the gas. So that's part of what I get paid that 20% for accounting. And it looks like this. So here's 3 producers, A, B, and C. Each one has a different flow rate. This one's got 1 million a day with a BTU value of this. Here's 500,000 a day with 1,000 BTUs. And here's 1.5 million a day with 900 BTU. So now we calculate a weighted revenue to be allocated. So to producer C, we'll use him as an example, he'll get, he's got 1.5 times 900. And that'll be his percent, this 1.5 times 900, of the total of the weighting of the others, of all 3 total. Got it? So this producer here that has 1.5 million a day at a BTU value of 900 BTU per standard cubic foot will get 48.5% of the revenue that's generated allocated back to him based on his volume and heat value of his gas. And it gets to be very complex in the field. All those allocations have to be made. These 4 producers may be selling at one point. The next 2 rows may be selling at another point. So then they've got to allocate it back to those points and then in turn to the individual producers.
So, John, did anybody change throughout the last 12 constant?
Usually it'll stay constant. You want to check it if you do a workover. You want to check it if you recomplete to a different zone. But those tests may be taken every 6 months. This is a map of the natural gas pipelines in the United States. The red ones are called interstate, which means they can only move gas within that state. So here's Texas, big, lots of red in Oklahoma and the Panhandle of Texas. California's got a little bit. States without much production don't have hardly any at all. So if we have gas moving, we take it up here to Oklahoma to Waha, not Waha, but Henry Hub. This is the Waha hub, and Houston Ship Channel is down here. Gas has to keep moving to sell. We don't usually store gas anywhere, except on these lines going up the East Coast, and like that. In these areas are some depleted old gas fields. And gas will, in days prior to the Marcellus and the coming on of that large volume of gas in the east, that gas would go into these storage fields here through the summertime to be stored. Then when the cold winters would hit in New England, they'd pull gas out of those caverns and take it up. And so there would be cyclical ins and outs of those caverns, and on price, depending where you stored it at, what price you get when it got cold in New York City. They were willing to pay more for it then. Look at the collection of pipe now in the Marcellus as a result of shale gas. So they have now more pipelines closer to where these big markets are right here. The only trouble is they're getting a lot of environmental pushback on land pipelines. So this is still a dependency on gas coming out of here. You got to know where your market is, where you can sell it. You can get into swaps, trades. You can sell your gas here, sell it to a company that'll move it up somewhere else so you make more money. And then we're going to talk about hydrates.